Let's talk about sequential criterion for limits. Theorem. Let x and y be metric spaces. E is a subset of x. F maps E into y. P is the limit point for set E. Then the limit of f of x as x approaches P is equal to Q if and only if the limit of f of Pn as n approaches infinity is equal to Q for any sequence in E that approaches P. Let's take a look at the proof together. Suppose left-hand side is true. Suppose the limit of f of x as x approaches P is equal to Q, and Pn as a sequence in P approaches P, and Pn is not equal to P. What is our goal? Our goal is to show that the limit of f of Pn as n approaches infinity is equal to Q. Let's put a question mark here. This is what we're trying to prove. What we have are these pieces of information. Let's apply direct proof. We know that the limit of f of x as x approaches P is equal to Q by using the definition of limit for any positive epsilon, there is positive delta such that the distance between x and P is less than delta, then the distance between f of x and Q is less than the epsilon that you have. So this is the definition of limit. What we also know is that Pn approaches P. Definition of convergence of sequences. There exists a natural number like n such that for any n larger than n, the distance between Pn and P is less than the delta. And this is a positive distance as well. So let's compare these two statements together. It says the distance between any x in E and P is small. You have a small distance. You have a small distance between Pn and P, and remember that Pn is a sequence in E. So you can easily substitute these two. This x and Pn. So the distance between, instead of x, we're using Pn. The distance between f of Pn and Q is also less than epsilon, which means that the limit of f of Pn as n approaches infinity is equal to Q. So we just proved that the limit is Q. Now the other side of the proof. Now suppose that your right-hand side is true, we want to try to prove the limit is equal to Q. Suppose the limit of f of Pn as n approaches infinity is equal to Q for any sequence like Pn approaches P. Our goal is to show that limit of f of x as x approaches P is equal to Q, a question mark next to it. Let us use proof by contradiction. Suppose not. And the limit is not Q. A limit of f of x as x approaches P is not Q. So by assumption, this is not equal to Q. What's the meaning of that? Recall that in the definition of the limit, let me use a different color here. We say that the limit of function f of x as x approaches P is equal to Q. It means that for every positive epsilon, there exists a positive delta, such that when the distance between x and P is small, then we can conclude that the distance between f of x and Q is small as well. The negation is going to be as follows. The negation of for all is going to be there exists, so you can find a positive epsilon such that for any delta, remember that when you have A, then B, it is equivalent to not A or B, and the negation is going to be A and not B. So for any positive epsilon, now converts into there exists. There exists a positive epsilon. There is a positive delta for any delta. A, which is the distance between x and P, is small, but and the distance between f of x and Q is not small, getting larger and larger. So this is what we have. Very good. The limit is not equal to Q. The meaning of that is, as we mentioned before, step by step, there is a positive epsilon such that for any positive delta, the distance between x and P is small, but the distance between f of x and Q is not small. That's the meaning of the limit not be equal to Q. Remember that we have some pieces of information that we have here. We know that Pn approaches P and the limit of f of Pn must be equal to Q. So what are we going to do? We're going to do the following. We're going to say that for each n as a natural number, let delta be 1 over n. So for each n, we can define Pn, all right? Pn belongs to set E. And it has the following property. The distance between Pn and P is small, but the distance between f of Pn and Q is not small. It's larger than equals to epsilon. But it contradicts with the limit of f of Pn must be equals to Q. So where did the contradiction come from? The contradiction came from the assumption that the limit of f of x as x approaches P is not equal to Q. So limit of f of x as x approaches P must be equal to Q. So we just prove this theorem.